Chapter 14, Section 1, Part 2. Part 1, we talked about, here's what's happening in glycolysis as an overview, and then we looked at the actual enzymatic reactions. How are the electron bonds being rearranged in each of the reactions of the preliminary or investment phase of glycolysis? Here in Part 2, we're going to be looking at the payoff. Okay, preliminary or the investment, you invested some ATP, changed the shape of glucose into a fructose, and then cut it in half. So here, we're going to be looking at what happens to G3P, the glyceraldehyde 3-phosphate. We're going to see some oxidation at carbon 1, going to lose some excited electrons / hydrogens. So NADs will be reduced to NADHs, and then we're going to go get some of those inorganic phosphates back so we can generate some ATP. So first off, glyceraldehyde 3-phosphate dehydrogenase. Okay, glyceraldehyde 3-phosphate dehydrogenase. This enzyme is going to take G3P and free-floating inorganic phosphate. This is not associated with any ATPs, ADPs, AMPs, whatever. It's just in the cytoplasm. It's also going to, in the process, take NADs and reduce to NADH. Going to take this hydrogen right here, add them to NADs. It's going to take this phosphate and add it to that same carbon, generating 1,3-bisphosphoglycerate. This is a very endergonic reaction. Okay, we're still using some of that energy that was imbued in the system by the addition of those ATPs, the addition of those phosphate groups from ATPs in the preliminary or investment phase. This is an energy conserving. Okay, we are making formation of an acyl phosphate group at C1. Okay, when we go and we take that energy, we remove that phosphate group, we take that energy, there's a lot of energy there, okay, in that acyl group because it's carbon, double bond oxygen, and an inorganic phosphate. So it's a carbon, carbonyl, inorganic phosphate there. There's a lot of energy there as we see here. The way this is working, okay, glyceraldehyde 3-phosphate dehydrogenase. Okay, in the active site there is going to be cysteine that has a sulfur group. Sitting right there, that sulfur group is going to do a nucleophilic attack on carbon 1, as we see right here. Carbon 1 that has a carbonyl group right there, we're going to see the shifting of its electrons, bonds. Shifting of the bonds, going to release one of the bonds, bind directly to the sulfur of the cysteine. Okay, this electron pair here between carbon and hydrogen and carbon 1, you're going to see this is going to be shifted to a neighboring held in place NAD. So we now have reduced NAD to NADH, and we have a 3-carbon glyceraldehyde G3P intermediate that is bound via sulfur bond here to cysteine in the active site. Going to do this again. More NADs, going to be involved here. Swapping the NADH for NADs. Going to bring in another inorganic phosphate at the same time. Notice again, I'm going to keep reiterating, keep saying this over and over. This is not attached to anything. This is a free floating that the enzyme is going to take up on the active site along with our organic molecule here. And we're going to see the shifting of the electron bonds again. This carbonyl group here, this oxygen is going to attack the carbon. We're going to see the electrons going to be released here and shifted over to this incoming inorganic phosphate group. 1,3-bisphosphoglycerate is released, and hey, look here, G3P dehydrogenase is reset, NAD being ready to be reduced, and the sulfur group is back to being S-. Everybody's happy. Now we go through and we take this phosphate that was just added. So we're taking a phosphate group, we're adding it to G3P, making bisphosphoglycerate, and then the next step we're going to strip that phosphate right back off. Why did we do that? Why didn't we just add it directly to ATP? Energy. By putting it into this system here, this carbon with the carbonyl and this right here, remember that had a really nice low negative delta G, kilojoules per mole. Just by taking that inorganic phosphate and adding the ATP, yes, there'll be some energy there, but nowhere near as much. So something about putting it to this bond, and yes, you go ask, a molecular physicist, you go and ask an inorganic chemist, they can sit there and explain the different electron orbitals that would be impeded or stressed, or how everything's put into a higher energy phase because of everything here attached to this carbon. I don't know all those things, so I'm not even going to try to explain those things. Just by adding it here, all I know is it increases the amount of energy, lowers that delta G, makes it even more negative. So phosphoglycerate kinase is going to take this phosphate group off of carbon 1, add it to a diphosphate to make a triphosphate with negative 18.8 kilojoules per mole imbued into that reaction. Like I said, this is what they refer to as a substrate level phosphorylation. You're taking a phosphate off of something via an enzyme and adding it directly to a diphosphate to make a triphosphate. As in all things enzymes, it's fast, it's reliable, but it's not quite as clean, it's not quite as efficient as what we're going to see in later chapters when we talk what's occurring in the mitochondria. So our sum here, G3Ps plus A diphosphate plus inorganic phosphate plus NAD yields us phosphoglycerate plus some ATP plus some reduced NADs to NADHs and some free hydrogens. Negative 12.2 is what our two steps. So yes, one step by the adding of the phosphate group was exendergonic, but when we remove it, is very endergonic, yielding us a nice surplus of energy. Now we need to, as I always make the stupid analogy, stupid joke, we need to rearrange the furniture. Because think about it, in your room, you're not, if you just got tired of your room, you're not going to go out and buy new furniture. Well, most people don't. You're not going to just throw away furniture. What you're going to do is you're going to rearrange the furniture to at least make the room have a different appearance. It's still all the same furniture, it's just in new places. Same thing here. We're not adding things, we're not taking things away, we're just moving where they're associated with. This phosphate group that's associated with carbon 3, hence 3-phosphoglycerate, we're going to shift things around. Going to move it up to carbon 2 now. Carbon 3 is now going to have a hydroxyl. This takes energy. Good thing we have some energy right there. The way this mutates, enzyme mutates. It changes what's there, but it doesn't add, doesn't subtract. What we see here in the active site of the enzyme, histidines. The nitrogen of the R groups of histidine are going to do nucleophilic attacks on the hydrogen. We have a phosphate group here that's pulling off or it's attacking this electron pair here. So you're going to get shifts. Pull off the hydrogen. This phosphate group that's here on this histidine is now going to be interacting directly here via this carbon. And you're going to get shifts. Boom. So this phosphate group from this histidine in the active site is now associated with carbon 2, and the phosphate group from carbon 3 is now going to start interacting here itself. And we see the shifting of the electron pairs, and boom. So ultimately, the phosphate group that is now associated with carbon 2 of our glycerate molecule initially came from the enzyme itself. It's not that 3 was plucked off and then put onto 2. No. A phosphate group from the amino acid sequence, from an histidine amino acid, R group, in the mutase active site, gets added to carbon 2 to replenish, to reset that enzyme. The carbon 3's phosphate group is plucked off and then added there. So that's what we can see here. They've just swapped around. To phosphoglycerate to our friend glycerate, or phosphoenolpyruvate. So we're going from phosphoglycerate to phosphoenolpyruvate. How do we do this? Well, we need to remove the hydroxyl. Enolase. Enolase is going to come in. It's going to remove this hydrogen, this hydroxyl, 2 H's and O, releasing water. So this bonds here, we see here, these electron pairs are now going to go between carbon 2 and carbon 3. More substrate level phosphorylation. Taking this phosphoenolpyruvate, pyruvate kinase is taking this off, adding it to a diphosphate, yielding ATP and pyruvate. And here is that reaction. We've talked about this last chapter with negative 31.4 kilojoules per mole. Turns out, and if you look at this phosphate reaction has a lot more energy imbued in it than when we looked at the beginning here of the payoff phase, when that inorganic phosphate was added to G3P and then 1,3-bisphosphoglycerate generated, and then that phosphate group was immediately pulled back off. That had, yes, a lot of energy there, but definitely not to this level. And then, as we talked about at the end of chapter 13, the pyruvate, well, it's not a set form, not a set structure. There's an enol and a keto. Enol, keto, hydroxyl, carbonyl. You get this tautomerization, back and forth. Yes, the keto form seems to have going from the enol to the keto form seems to have a stronger push. Remember we talked about with the E naught in the last chapter. There seems to me want to go more one way than the other, but it is also reversible going from the keto back to the enol form. So overall, what we're looking at here for all of glycolysis, glucose plus 2 NADs plus 2 ATPs plus the 2 inorganic phosphates. Remember, these inorganic phosphates are actually here, and it's 2 ATPs. Yields 2 pyruvates, 2 NADHs, 2 free hydrogens, 2 ATPs, and 2 waters. If you remember back to your freshman biology and your cell biology, it's invest 2 ATPs, that's what these are together, and in all honesty, you get 4 out, because remember it's 2 ATPs that are generated for each G3P, total of 4, but you invested 2s, and you're yielding 4, or coming out with 4, net, or gross, net, I keep getting those, 2 ATPs.